Hello everyone. Welcome to an introduction to object-oriented programming. In this course, we will be getting into what object-oriented programming means, as well as going over its four main principles. This course will assume that you have some knowledge of programming before hopping in. If that's not the case, I would suggest checking out our Introduction to Programming video, which will be linked in the description. That video will give you information on the basics of programming that are necessary to be able to understand more advanced topics, such as those covered in this video. For this lecture, we will be exploring object-oriented programming in a manner that will be applicable for its use in any programming language in which it is supported. Examples will be used to explain the concept being discussed. However, they will be explained well enough that specific knowledge of the language being used in the example will not be necessary. With that being said, let's get into it. In this first section, we will be going over what object-oriented programming actually is. In order to understand what object-oriented programming is, it's best to first understand what objects are. And in order to do that, it's best to first understand what primitive data types are. So let's start there. Primitive data types are exactly what they sound like. Variables that store single, simple values. Examples of such primitive types are the byte, int, float, double, boolean, and char. These primitive types only act to store a single piece of data of a certain kind. And for a while, when programming was still developing, this was just fine. Many programs being written at the time weren't complex by today's standards. Thus, programmers could get away with only using these primitive types. However, as programs became larger and more complex, primitive data types weren't really cutting it anymore. Programmers began to want to group variables of similar type together. Why would this be useful? Well, to serve as an example, let's imagine you are trying to program a chess game. When programming a knight into the game, there are plenty of variables that you will need in order for the piece to work how it should. For example, you would need a position variable to keep track of where the knight is. Additionally, you would need a boolean to represent whether the piece has been captured or not, because if it has, you would not want it to show up, nor should you be able to move with it. You may also need a variable to represent which color the knight is, so that the game can treat it correctly. These are just a few of the variables that you would need for one piece, and you would need one of each of these variables for each piece on the board, each of which would contain different data. Clearly, it would be easiest if you could group all of the variables related to, say, one of your knights together, so that you may deal with them as one entity. Additionally, you may want to group your two knights together, as they behave similarly. You then may want to group the pieces of each side together, as they would be treated differently in reference to each other. In essence, grouping related variables together is almost necessary when it comes to complex programs. This is where the struct, or structure, came in. In C, the structure is similar to an array. If you don't know what an array is, I'd suggest you check out either our Introduction to Programming course for an overview, or our data structures series for a more in-depth look at both arrays and many other data structures. Both arrays and structures allow the programmer to store several pieces of data together. However, structures vary from arrays in that structures allow the programmer to store data of different types together. For instance, whereas an array would allow you to store only ints or only strings, using a structure, you could store ints and strings together, along with other data types. A structure can even store other structures within it. A structure can be very useful in the earlier chess example because you could store all of the useful pieces of data related to the knight in one structure that represents that knight. You could then store your knight structures together in one structure that represents all of the knights, and so on. The structure allowed such grouping to take place beyond what arrays were capable of. The structure is, in many ways, the precursor to the object, which, of course, object-oriented programming is oriented around. The main issue with using a structure in this way, and an issue that objects would come to remedy, was that you could not define functions within a structure, you could only reference them. When object-oriented programming came along, objects allowed you to store data of all kinds together, and, additionally, define and store functions. Now, before we go much further, I should get into exactly what objects are. Objects are instances of a class, and a class is basically a template for an object. This may seem like a circular way of looking at these concepts, but allow me to explain. Let's say I define a knight class. In this class, I would define and store data that is common of all knights. This would be, mainly, the way that knights are able to move. Thus, in this class, I would define a function that uses the knight's current position to return squares that the knight can move to. I may also define a position variable, as well as a color variable, but I would not initialize them. When it comes to specific things, such as variables that each object under the class, in this case each knight, would have different data for, it's best to define them when I create the object, rather than in the class itself. For instance, each of the 4 knights that begin in a game of chess start on different squares than one another. Initializing the position variable in the knight class would imply that you want each knight object created from this class to begin with the same position, which you do not. However, each of the knights would behave the same in terms of the squares it could move to based on their position, and thus it is best to define a move function in the class rather than repeating the same function definition in each object that I create. When creating a knight object, you initialize its attributes, or its variables, and its methods, or its functions, to contain information specific to that knight. Whereas the knight class represents any given knight, a knight object represents one knight in particular. Essentially, object-oriented programming is the best tool us programmers have right now to create complex programs by grouping together related data and functions. Throughout the course of this video, we are going to be getting into detail into how all of this works using the 4 main principles of object-oriented programming, those being encapsulation, abstraction, inheritance, and polymorphism. This next section is going to be focusing on the first of the 4 main principles of object-oriented programming, encapsulation. Encapsulation refers to bundling data along with methods that can operate on that data within a class. Essentially, it is the idea of hiding data within a class that anything outside that class cannot directly interact with. That is not to say that they are unable to interact with a separate object's attributes at all, however. Instead, members of other classes looking to interact with the attributes of an object should only be able to do so through that class's methods. In practice, one way this tends to work is by creating getting and setting methods. These methods act to either get information from an object or set attributes to different values. For instance, think back to the chess example from the previous section. If I was moving one piece and I wanted to determine whether it was able to capture another piece, I would need to define a .get method associated with each piece that returns the piece's color, in this case, piece.getColor. This way, I could check the color of any piece from anywhere in my code without having to access the internal attributes of said pieces. This allows us to retrieve the information from where it is defined. Additionally, this makes it easiest to keep track of attributes that depend on one another. For example, if I was programming a game, I may have 2 different attributes for the player's health, max health and current health. When the character levels up, I may have their max health increase as well. When this happens, I would want the current health to be set to the maximum health. Instead of changing both of these values directly, I could define the setMaxHealth method such that the current health is also set to the maximum health once the maximum health has increased. Furthermore, these setting methods allow values to be validated. For instance, if current health is not able to exceed maximum health, then I would have the setCurrentHealth method check if current health would be greater to maximum health before making the change. Finally, you may want some values to be read-only from outside a class, which means you would only define a getter method and not a setter method. For another example, let's look back at chess. When dealing with a piece's position, you would want to keep track of its rank, or its row, and its file, or its column. When the piece moves, you may think it would be okay to just set piece.rank and piece.file to new values. However, as discussed above, this is not the best way to handle it. It would be better to define a piece.move function that takes the intended new position and checks if that is indeed a valid move. The piece would not be able to move if, say, the new location is off the board, a piece of the same color is already on that square, or making such a move would put the king of the same color in check. Additionally, other methods may be called from this move method, for instance, one that captures an enemy piece if it was on that square, or one that puts the enemy king in check. Were the piece's attributes just to be directly changed, you could end up in a strange situation where illegal moves are played and pieces occupy the same square. Essentially, getter methods allowing validation can be very useful. Encapsulation is useful for a variety of reasons. As we just went over, it is best to not allow anything external to directly edit an object's attributes. This is especially true when working on large and complex programs, where you may want individual pieces of the program to work well without requiring them to rely on every other section of the code. In this way, preventing each piece of your code from referencing and requiring knowledge of the inner workings of each other section of code is very important to keep your program from becoming completely entangled in itself. This is an idea we will touch upon in future sections to come, but for now it's best to understand that information hiding, that is, keeping one class from being able to directly access the data of another class, is important to keep control of your program and reducing its overall complexity. Overall, encapsulation is a vital component of object-oriented programming that allows the programmer to maintain control of their data and to keep their program from ending up in any unwanted states. In this next section, we are going to be discussing the next of the four main principles of object-oriented programming, abstraction. Abstraction refers to the idea of only showing essential details and hiding everything else. This idea is present in everyday life. When you drive your car, there are some things you need to understand about it. You need to understand how the steering wheel steers the car, and how the gas and brake pedals work. You also need to know how much gas your car has, and that it needs gas to work. These are necessary details for you to be able to drive the car properly. However, the exact way that the car works internally isn't something that most people need to concern themselves with. How the gas reacts in the engine, and how that translates into the car moving forward, really isn't important while you are driving your car. All that matters is that you know it will work this way. Whoever built the car had to worry about how exactly the car would work, so that you don't have to. This idea extends to object-oriented programming. The classes you create should act like your car. Users of your classes should not worry about the exact inner details of said classes. This idea is similar to that of encapsulation that we discussed in the previous section. Earlier, we mentioned how you should not have classes directly interact with the data stored within other classes. Rather, have them use the class's methods to access their data. This idea is especially important when you want to work on your program incrementally, where you focus on one class at a time and ensure that it works. This is a very useful approach, as it can be difficult for you to focus on the big picture while programming, and splitting up your project into smaller chunks can make it much more manageable. Furthermore, programs nowadays are vast and complex to the point where multiple programmers tend to work on one project. In this case, it's best if the section that you are working on is able to function without knowledge of the inner workings of your colleague's section. To achieve this, it's best to think of your program in terms of interface and implementation. The interface refers to the ways that sections of code are able to communicate with one another. This is typically done through methods that each class is able to access. The exact implementation of these methods, or how the methods are coded, should be hidden within the class and not accessible from the outside. Think of this like the car. The other classes are able to turn the wheel and push the gas, and they know what the outcome should be without caring about exactly how this gets done. Let's return to the chess example that we've been using throughout the video. Let's say that you are working on making the knight work as it should, and a fellow programmer is working in the king class. In order to effectively work together, you need to agree on an interface with which these pieces are able to communicate. In this case, say that you are working on making the knight unable to move if your king is in check. As the programmer of the knight class, you make the knight use the king's getter method that will let the knight know whether or not the king is in check. If it is, then you make it so the knight is not able to move unless it is able to put the king out of check. As you program the knight class, you should not be concerned with how the king is determining whether or not it is in check. The king's method that tells the knight whether or not it is in check is part of the interface, but how exactly it does that is part of the implementation. This manner of only allowing the classes to interact through a predetermined interface prevents different pieces of the program from becoming completely coupled together. If the knight class has to look into the king class in order to make a determination, then it is reliant on the king class being set up in a certain way in order to function. If the king class is changed or reorganized or its data is renamed, then the knight class would no longer work, and it too would have to be changed. Assuming the rest of the program was coded in this way, then many other classes would also have to be modified. Creating a set interface through which classes can interact with one another ensures that each individual piece can be changed without creating a ripple effect that causes the entire program to have to change in response. Overall, it's best to keep in mind abstraction when writing object-oriented code, as it allows the program to be worked on incrementally and prevents it from becoming completely entangled in itself and very complex. Determine specific points of contact that can act as the interface between classes, and only worry about the implementation behind it when working on that section. This next section will be tackling inheritance, the third of the main principles of object-oriented programming. Inheritance is the principle that allows you to derive classes from other classes. Classes can inherit certain methods and attributes from another class. We will get into exactly what this means in a moment, but first let's look at an example. Let's say you are programming a game. In this game, the player has access to weapons to fight their enemies. To begin, you may establish a weapons class. This class would contain many of the pertinent attributes and methods common to weapons. For instance, an attribute that represents the damage that the weapon deals, and a method that deals damage to an opponent when called. You then would want some more classes to represent specific weapons, such as a sword or a club. These classes would act differently from one another, as swords and clubs have certain different attributes, such as a sword being made for cutting, whereas a club is blunt. These differences would be represented in different values for their attributes, as well as possibly different attributes altogether. However, they do share much of the same behavior, as they are both members of the weapons class. In this case, the weapon class would be the superclass, and the sword and club classes that extend the weapon class would be subclasses in relation to it. Many of the attributes and methods associated with the weapon class would also be present in its subclasses. Any given sword or club would also want access to the methods that allow them to deal damage, as well as the attributes that detail how much and what type of damage they deal. The class hierarchy does not tend to be so small, however, as in most cases there are many more layers than just one superclass and a couple of subclasses. The weapon class may be a subclass to a broader items class, which could contain many other subclasses with subclasses of their own. Additionally, you may include a wider variety of weapons than just swords and clubs, as well as multiple types of swords that would require different behaviors and thus their own subclasses. When you are writing object-oriented code, many of the classes you create will fit somewhere in the broader class hierarchy, which acts as a web of classes with different relationships to one another. The next important topic to cover in terms of inheritance is the access modifiers that change which classes access which attributes, methods, or even classes as a whole. There are three main access modifiers that we will be discussing: public, private, and protected. Let's begin with the public modifier. Public is probably the most simple of the modifiers. A public member or class can be accessed from anywhere. This includes any superclasses, subclasses, or anywhere else in the program. This is very useful when you need to have access from a wide variety of places in your program. To better understand this modifier, and those to come, look to the example class hierarchy on screen that represents different foods. For each example, the member in question will be defined in the fruit class. Green classes have access and red classes do not. As you can see, a public member being defined in this class, or anywhere else, can be accessed from anywhere in your program. Next, we have the private modifier. Private members can only be accessed from within the same class that the member is defined. This is best to use if you do not need this information accessed from anywhere else in the program. Additionally, this allows you to create other private members of the same name in separate classes, which will not conflict with one another due to their private access modifier. As you can see on the example class hierarchy, a private member defined in the fruit class can only be accessed inside the fruit class. We then have the protected modifier. A protected variable can be accessed from within the class it is defined, as well as any subclasses of that class. Essentially, protected variables are private to the class hierarchy that they are defined in. This can be seen in the example class hierarchy right now. In this final section, we will be covering the final of the four main principles: polymorphism. Polymorphism describes methods that are able to take on many forms. There are two types of polymorphism. The first one is what is called dynamic polymorphism. Dynamic polymorphism occurs during runtime, when the program is being executed. This describes when a method signature is present in both a subclass and a superclass. The methods share the same parameters, but have separate implementation. In this case, the subclass's implementation of the method overrides the superclasses. Let's go over an example. Let's say you are writing a program to represent many different types of cars in a class hierarchy. At the top of the hierarchy, you may have the generic car class. You then may create a sports car class as a subclass of the car class. You then may create a .drive method in both of the classes. In each of the classes, the .drive function will take a double representing the number of miles you would like the car to drive, and the car's gas attribute will be decreased by the pertinent amount. In the car class, the .drive function may cause the car's gas to decrease by 0.04 gallons per mile, whereas the sports car class may instead have its gas decreased by 0.02 gallons per mile it drives. If you create an instance of a sports car called MySportsCar, the sports car implementation of the .drive method will override the generic car version of the .drive method. Therefore, MySportsCar.drive will decrease MySportsCar's gas attribute by 0.02 gallons per mile. However, were you to create an instance of the car class called mycar.drive would instead decrease my car's gas by 0.04 gallons per mile. This is an example of dynamic polymorphism, as the implementation of a method signature can change depending on which level in the class hierarchy that it is called. This works this way because the form of the method that is called is decided dynamically as the program is run. This idea can be extended across a class hierarchy in more layers than just 2. You could add more subclasses representing different types of sports cars with their own .drive methods with different implementations, and creating an instance of each of these subclasses would use their own implementation of the .drive method when called. The main benefit of dynamic polymorphism is that it allows you to write methods in the superclass without having to include ifs and else ifs to account for exactly which subclass is being used when the method is called. The second type of polymorphism is static polymorphism. Static polymorphism occurs during compile time rather than runtime. This refers to when multiple methods with the same name are defined in the same class. In this case, the methods are differentiated by their arguments. Either they take a different number of parameters, they take parameters of different types, or they take parameters in a different order than one another. This is known as method overloading. Despite the names of the methods being the same, they have different method signatures due to their differences in the parameters that they accept. To better understand this, let's go back to the car example. Let's say that you are working within the car class. In this class, you are looking to create 3 different drive methods. The first drive method's argument accepts 1 integer and 1 string as parameters, say speed and destination. For clarity, we will refer to this one as drive method 1. However, keep in mind that its method name is just drive. For drive method 2, we will set its argument to accept 2 integers, for instance, distance and speed. Finally, in drive method 3, we will have it accept a string first for destination, and then an integer for speed. This differs from drive method 1 in that drive method 1's parameters are in reverse order compared to drive method 3's. In each of these 3 example methods, the method signature is different despite the methods having the same name. Therefore, the computer is able to tell the methods apart when the program is being compiled. For example, were I to call mycar.drive45 work, drive method 1 would be called, as the argument given indicates that this is the method I would like to call. Furthermore, mycar.drive1560 would call drive method 2, and mycall.drive_school30 would call drive method 3. When implementing method overloading, the different methods tend to have separate but similar effects. Despite drive method 1 and drive method 3 taking the same parameters, it is likely that their implementation would be different and thus would achieve separate effects. Otherwise, there would be no reason to have both methods. Keep in mind that method overloading can cause trouble if you do not keep straight which of the method's implementations you would like to execute and what form of the argument is required to do so. Normally, if you call a method with too many parameters or parameters of the incorrect type, then the program will throw an error and you will be able to fix the issue. However, if you mistake the method's argument in such a way that one of the other methods with the same name is called instead, then you may not even be aware that you made a mistake. Overall, polymorphism simply allows methods to take on many different forms. It can be very useful in that it allows methods of the same name to exist both in the same class and in different classes. However, you must be careful to ensure that you are calling the correct form of the method that you want so your program can function as intended. That does it for polymorphism. And with the end of polymorphism, the final of the 4 main principles, comes the end of this video on an introduction to object-oriented programming. If you enjoyed, consider liking and subscribing to Null Pointer Exception, and check out some of our other videos, in which we cover a variety of other topics that you may find helpful. Thanks for watching.